So we're gonna go ahead and get started. Welcome everybody. Welcome in. This is the April version of the Next Generation Science Standards for Earth and Space Science webinar. And today we are featuring two wonderful presenters, one from Concord Consortium and one from UNAVCO. So we'll have two great presentations to hear here in the next 45-50 minutes or so. And then we'll follow that up with a little bit of discussion and conversation afterwards. So the organizers of this webinar series, which is a webinar series that happens every second Thursday of the month at 4 p.m. Eastern, 1 p.m. Pacific, are myself, Aida Awad. I'm at Broward College in Fort Lauderdale, Florida. I'm also past president of the National Association of Geoscience Teachers and currently the secretary-treasurer. Ed Robeck at the American Geosciences Institute. Ed is the Director of Education and Outreach. Sorry, Ed, I'm not really clear on your whole brand new title, so I'm not going to try to do that one. Carla McAuliffe, who is the Executive Director of the National Earth Science Teachers Association, and John McDarris, who is with CERC and NAGT and is also our web guru. So we'd like to all welcome you in. If you want to go ahead and advance to the next slide, John. We do have two speakers today. So we have Amy Pellant, who is a senior research scientist at Concord Consortium, and she'll be followed up by Shelly Olds, who's a science education specialist at UNAVCO. We'll leave some time at the end for discussion and Q&A, and also we'd love to tell you about some of the future events, which you'll see on our next slide. Upcoming May 17th. So May 17th is not the second Thursday, it is the third Thursday, so we're breaking with tradition there a little bit. So May 17th, you can go ahead and register now. Registration is open for that next webinar, which will be entitled Integrating High School Earth and Space Science into Chemistry Classes. And our presenter for that will be Martin Schmidt, who has done a lot of work with schools in Maryland and across the country, who is a teacher currently at McDonough School in Maryland. And he'll be taking us on a tour of the connections between earth and space science and high school chemistry that are called for the Next Generation Science Standards. He has some very interesting perspectives on how we can broaden chemistry to really include the important materials and processes of the chemically active earth. And this is really broadening it not only for the chemistry instructors, but also for earth and space science. So very interesting perspectives there. And the link to registration is there, and we'll be sending that out via email in the next week or so as well. Also invite you to jump onto our programming flyer. You can see a short link to it there that lists all of the webinars that we've done in the series, as well as any of the workshops, and gives you access to those resources. And if you'd like to have access to all those resources, please join our email list. Okay, next slide. So we're going to go ahead and jump right in. Once again, we would ask that if you do have questions down at the bottom of your screen, you use the chat window to enter your questions. And we're going to hold off on those till the end of Amy's presentation. So Amy, take it away.
All right. Share my screen. And hopefully, let me know, are you seeing something that says High Adventure Science right now?
Yep. Yes, we are.
Okay. And can you see me? All right, somebody's going to have to just pay attention to time. I'm not sure exactly how long I'm going to end up talking, and I just don't want to take up too much time. So I'm going to be talking about High Adventure Science. High Adventure Science is near and dear to my heart, so I'm very excited to share it with you. So who am I? So I'm Amy Pellant. I work at the Concord Consortium. And the Concord Consortium, for those of you who don't know who we are, is a nonprofit that is in Massachusetts. And its mission is to change teaching and learning by incorporating the best features of digital technology in STEM education. It's been around for 25 years. I've been here for 18 years, working on a whole host of different NSF projects. But Concord Consortium has been a pioneer in technology and education. It's the first place to do online education and spun off the virtual high school from here. So it's the first place to do distance learning. We pioneered the use of probes in classrooms and worked very closely with helping Vernier, et cetera, for using probes. And we're also leading the use of online computational models for education. So what is high adventure science and how did it get started? What inspired us, or me, when I wrote the proposal, at the time I had been reading a lot about, what makes science fun. And I read this quote by Lewis Thomas, which is, very few people see science as a high adventure. It really is, thus the name. But also that, this idea of, exploration and research is very different than the way things are often done in classrooms and education, which is memorize the right answer, and do cookbook explorations. And at the same time I was reading that, Science had their anniversary edition that came out, and it was the anniversary edition, which had the 125 questions about what we still don't know. And we would sit around at lunchtime here at the Concord Consortium, and these were one-page articles, and we found them really interesting and exciting about what was known and what was still yet unknown, and where the frontier of research was. And we wanted to think about, is there a way that we could, in fact, excite students about what's happening at the frontier of research in the same way that we were? And that was sort of the birth of the high adventure science proposal. And what we thought is, are we able to leverage what is still unknown in research and bring that into classrooms? We proposed modules that came from the questions in that science magazine. And here are the ones that we thought that we could bring to the classroom and include and incorporate Earth systems models to help students learn about it. And the modules focus on freshwater availability, the search for life in outer space or finding habitable planets, air pollution, the future of Earth's climate or climate change, can we feed the growing population, and what are our energy choices? And you can see that a lot of them are related to human impact on the environment. And this is leads into, we tried very hard to look at the next generation science standards and make sure that we were bringing in materials into the classroom that are related to what students needed to learn, the core earth and environmental science concepts, but had aspects of, what's happening at the frontier of research. And so we correlated all of these modules to the core ideas in earth science, and you can see that the next generation science standards actually have core ideas that focus on human impacts on Earth, global climate change. And so, we are addressing the core ideas, but also each of the modules address cross-cutting concepts and science practices. What you can see here is that we've only highlighted a few of the cross-cutting concepts and the science practices. In fact, I know that you can find other cross-cutting concepts, but we were explicit about helping students think about cause and effect in Earth systems. And while we're using Earth systems models to learn about it, to look at systems and systems models. And similarly, engaging students in argument from evidence and analyzing and interpreting data. And I'll explain more. When you look at all of the modules, each one, which is, I will emphasize, is free and available online to anybody, follow these design principles. They're 5-day-long modules and 5-day, 45-minute periods. So depending on how you teach and what level you teach, you can do it longer or shorter if you have block periods, etc. But that's how we design these modules. And all of them, they start with those framing questions that I showed you a few slides earlier. We incorporate real-world, real scientific data. Science, they're not been simplified in any way, so that's an important thing I'll talk about in a minute. They all incorporate and use computational models that students can interact with the models. And then they engage students through scaffolding in the modules into systems dynamic reasoning and evidence-based argumentation. So here's examples of some of the data that we incorporate. And you can see that what we have done is the data is represented in a whole host of different ways depending on the content area that the students are exploring. And as such, students need to start to interpret data in this various representation. So it could be a map representation, it could be a pie chart, it could be a graph. And if you look at the climate data up here in the upper left, we don't change anything. So it's talking about temperature anomaly, and it has a lot of data and a scale that is not necessarily familiar. So we provide scaffolding to help students try to make sense of it, and also provide for teachers you know, what we expect from students with regard to it. And similarly, you know, that we're looking at trends, we're looking at can you interpret data in different ways. The thing that we spend a lot of time on here is developing these computational models. And why do we do this is it allows students to experiment with things that might otherwise be impossible to experiment, and look and explore topic areas and variables in a way that is similar to a lab-based experiment, but in imagining in earth science, it's often too big or it takes too much time that you can't bring it in, where computational models allow students to have the same sort of experimentation. And it allows them to get insight into causal mechanisms, even if it's not a linear mechanism, but they can see correlations. So, you know, it makes it possible for students to experiment where otherwise they can't. They get to change variables and see the emergent phenomenon. And with the educational models, we provide both visual, you know, and easily accessible graphics, but we also provide emergent data so that the students can then interpret what they can view visually in the model on the left, as well as the graphs on the right. And with that, we scaffold students to help them gain evidence, take evidence from the models, and use that for developing their understanding. I'm going to show you just an example or two of models. Can you see this model now? Did it switch for you guys? Somebody?
Yes, Amy.
Okay.
You might make it, if you can make it just a little bigger on your screen, that would be good.
I will try. Is that bigger for you guys?
Yes.
All right. So here's an example of an online model. This is for students to explore what factors affect air pollution in an area. And what you can see is that there's variables that students down here can change. They're going to explore the relationship to the environment, so they can change the amount of rain, the amount of sunlight. They look at how mountains might affect where pollutants can flow. They can change the wind, and they also can change the amount of pollutants that are in the environment. So students can add cars, or they can add power plants, and pollutants come out as they're experimenting, and they can have wind coming from onshore or going offshore. They can change the sunlight, and so by changing the sunlight, it means that the angle and the amount of summer versus winter, such that they can see the primary and secondary pollutants that come in, change rainfall, so if there's no rain versus a lot. And through each of the changes and variables, students can see output on a graph. What we do in our modules is we will have variations of this model, but only provide certain variables for students to explore, so they don't change everything all at once. We teach them how to experiment with models. Similarly, here's a one that looks at soil quality, where students can change the terrain, and they can change what's growing on each side of the terrain. They can change the climate, and as they run it, they will see erosion rates based on what is growing and what's not growing. They will see how the amount of topsoils that change in different zones. They can see the precipitation that changes, and by exploring what's happening with the data, we then scaffold students to think about what is the evidence about that they can get from the model. So let me go back to the kinds of scaffolding that we have. So part of what we do is we support students to engage in systems dynamics thinking. And what I mean by systems dynamics, we have questions that focus on stocks and flows in the system, on feedback loops, on time delay, and all of these are aspects of system dynamic thinking that is important when you're understanding an Earth system. Imagine in that agricultural model where we're wanting students to think about the erosion, and so that's the resource that we're wanting them to focus on. So we ask them, what's the most important resource? We've set them up a little bit. And then what are the processes that are changing the availability of that resource? So all of a sudden they're now looking at how that resource is changing in the environment. And how are there things that might affect the changing of that resource? And in this case, for example, students are thinking about the kind of human impact and tillage, and how these management plan might affect the system. So you can see that we slowly help them think about the resources and what affects the resources. So the cause and effect is there, systems thinking through the systems model is there, and in particular we have items that are specific to scaffolding that sort of reasoning. Similarly, we look at argumentation from using evidence. And in education, claim evidence reasoning has become a very interesting tool for teachers and students to be thinking about how to develop scientific arguments. And the goal is to help the students focus on the reasoning necessary to coordinate the evidence with knowledge. But we have found that when you bring in unknowns or the frontier in science research, that there's critical reasoning that has been left out. And it's the uncertainties that, we have seen, for example, climate scientists say, I am not going to predict with 100% certainty exactly what's going to happen. They use uncertainties in how they talk about research, as most scientists do, because it's on the cutting edge. It's not 100% certain. So we thought it was important to include uncertainty as an explicit part of the argumentation reasoning. To do that, we developed something called the uncertainty-infused argumentation item set. That's a big mouthful. Kids don't need to know it, but it is a 4-part argumentation set of prompts embedded in the curriculum, typically around when they're interpreting scientific data and models. And the 4 parts include a claim. The students need to make a claim, and that's typically a short answer or a multiple choice where they have to just put their stake in the ground, like, this is what my scientific claim is. Then we ask them to explain, using evidence from the data or the models, why they chose that claim. So they're now reasoning about the evidence they're using. We then explicitly ask them to rate how certain they are about the claim and the evidence. So they do that on a Likert scale from very certain to not certain, and then explain what influenced their certainty rating. In the module, at the very beginning, there is a short activity that takes them through what is expected in each of these 4 parts of an uncertainty-infused argumentation item set. So how do you write an explanation? How do you write your uncertainty attributions? And you know, you can see this is actually one of the students asking, like, what do you want from me? You keep asking this question. And the teachers, you know, see the questioning from the students, because there often is not here is the right answer, the expectation of what your uncertainty rationale should include. But what we have found from our research is that, and we've conducted research for 8 years now with 53 field test teachers and over 4,000 students, is that this, by including uncertainty, we see that students typically start with their own personal uncertainty, like, I don't know enough about the subject, or I'm not sure I interpreted the graph correctly. And as they get better at it, and these argumentation item sets, there's usually 8 to 10 in every module, so over 5 days, they start to learn about including the strengths and weaknesses of the evidence that they've been using. So, for example, our educational grade models are in fact limited, and because we're trying to simplify the cause and effect relationships, so they can use that as the model shows X, but you know, in the real world, I'm not so sure, I'm not as certain how well this model is representing the complexity of what it's representing. So, you know, they're starting to think more like scientists would. And we also found that exposing students to these Earth systems models and getting them to focus on the variables and the evidence, that they actually start to think about the processes that are changing the systems and the resources, and they start thinking more systems dynamic-wise. I'm not going to go over the numbers specifically here, but there is significant improvement for the students, both in content as well as in argumentation and systems thinking skills. What I can tell you is that beyond even our field test teachers, these modules have been tested in all 50 states in the United States and other countries. And we have several 100,000 people now looking at these modules and using them. So I'm going to quickly also just show you what does our module look like. Here's the what is the future of Earth's climate. You can see that there's constructing an argument. That's the how do you do an argument. And then each of these is one activity. And we say approximately 45 minutes for one of these activities. When you click on one of the activities, what you will see is introductory text. Of course, as my computer model, it loads. This is a, a climate model where students can, interact with the model. And there's questions that scaffold their understanding. Students can type directly into the computer, and if you are registered as a teacher, you get to see all your student responses in a portal. So you can, all of student work is persistent. They go away, they come back, all of their answers are still there.
Amy?
Yeah?
This is Carla. So I'm noticing that it's 4:28 and we want to pass things over to Shelly. So we'll have a little bit of time hopefully for questions at the end, but thank you. This is, these are wonderful modules.
Okay, let me give you one slide more.
Okay.
This slide here is resources. This is how you find the resources. I know that these slides have been posted so that if you're interested in any of the modules, please head over there.
Great. Thank you, Amy. That was great. So we're going to hold questions until the end, and we'll go ahead and swap screen sharing privileges over to Shelly Olds from UNAVCO. Shelly, can you share your screen? Perfect. Got it.
And I will unmute myself too.
That's a good idea.
Awesome.
I'm going to go back on mute. And we'll give you about a 3 or 4 minute warning.
Awesome.
And Shelly, you can make that full screen if you just put it in presentation mode, I think.
Yep.
Okay, and I should be sharing my video. I don't know if I am.
I see your PowerPoint.
Okay. So I'm starting my video. So many different things.
Perfect.
Here we go. So the original title of this talk was Explore Plate Tectonics Through GPS Data. And as I put it together, I realized, well, there's and more, because it's more than just plate tectonics that we cover. Thank you, everyone, for joining us today. I'm Shelly Olds from UNAVCO, and here's a brief outline of what I'll be covering over the next 20-25 minutes. I'd like to have you keep in your mind the central question of how do we know the tectonic plates are still moving, and what evidence do we have for that? And then I'll go over a little bit about UNAVCO, because most folks aren't familiar with that, our organization, resources available through the Education and Community Engagement Group, and then go a little bit more into activities and modules and talk about how there's like different levels of explorations. So UNAVCO. UNAVCO, the mission statement is there. We're a nonprofit, university-governed consortium. We facilitate geoscience research and education using geodesy. And the pictures that you see around the edges of the screen show a little bit about the different kinds of science and the people we interact with. On the left-hand side is a velocity vector map, and we'll see some more examples in a little bit. In the upper left is a GPS unit that is permanently installed into a ridge. And that has been a big part of the work that UNAVCO has done through the Plate Boundary Observatory, was to install a network of permanent GPS. Very similar to what's in your handheld, except that these stay in place and move as the Earth moves, and their resolution is down to the millimeter level versus 1 to 3 meter resolution of accuracy. And then you can see we do a lot of workshops. We work with students, and I'll go into that a little bit. We've done some exhibits, and then you can see a project where they were scanning the flatirons in Boulder, Colorado, for using a laser scanning system. So we have 3 different program areas. Geodetic data services, so that's the data part of our life. And then we also have, and I'm putting on a timer so I don't get behind time, geodetic infrastructure, so that's the hardware, the equipment that we put out into permanent installations or even temporary installations. And then education and community engagement. This is actually at the Boulder's Farmers Market. And so that's pretty cool. Students and people, anyone can come up and we have these demonstrations going on. Some of the discoveries through geodesy have been in many different fields. Our bread and butter used to be in crustal kinematics and mantle dynamics. So how is the mantle moving? How is the earth moving? And from there, we've discovered, our community of scientists have discovered that you can also do some hydrogeodesy, looking at the water, groundwater movement, looking at the signal as the GPS signal comes through the atmosphere from the satellites. You can do some meteorology, fair amount of meteorology. We can look at how the glaciers are moving. Of course, the societal impact of like earthquake hazards, volcanic deformation and hazards, and then GPS seismology. So this is the group I work in, education and community engagement, and I have worked at UNAVCO 11, 12 years now, close to the time that the education group was put together, and I've been an education specialist here and at other places developing educational resources that are freely available to the public. And this is our homepage for the education area, and you can see that there are multiple areas. It's long enough that it goes beyond the fold. And so I'll now show you some of the resources that are available to you, both as a secondary level teacher as well as a college faculty, or maybe even as a researcher. So one of the areas that has been a big emphasis has been providing student opportunities to help with geo workforce development, and particularly reaching students who come from historically underrepresented backgrounds in the geosciences, and that's been through the Recess program. Then we've been reaching down into the lower division undergraduate for Geo Launchpad, and we're trying to tie into some other programs that are K-12 oriented. And then UNAVCO's student internship program, USIP, kind of does this bridging between upper undergraduate to graduate students. But then through postdoc early career, we have some short courses and early career resources, and then faculty mentoring, since students end up being paired with either scientists or folks here at UNAVCO. And so being able to mentor students is a really important component of the students' time in a program. And so we've developed some resources and pulled in resources from around the country. And there we go. And then, as I mentioned, there are short courses and webinars, and they are not just for the postgrad level. Those are covered under the geodesy technical tools. But we also have courses that are geared to be used in undergraduate and secondary level applications. And some of these titles are from last year, using different techniques within the classroom or field course, using recreational drones in STEM explorations. That was a lot of fun to create and do. And then using GPS data in undergraduate courses. But also over the last 2 years, we've now been also focusing on communicating science, helping people, scientists and others who are maybe maybe behind that, in that ivory tower, to get beyond that so they can reach the public and to other communities other than graduate students, to help give them resources and experience in communicating their science in ways that has a broader application. So what are some of the resources we have? Well, we've developed a number of different animations and career spotlights that are on YouTube. And these can be used in the classroom for students to explore different career paths. Up in the upper left, we have one student, Melissa Burt, who went through basically her career path to date, and now she has a PhD. And in the lower right, another student talking about her path within recess and then moving on beyond recess. And then animations, we recently made one about what is geodesy and the uses of geodesy. And then you see the animated GIF, which is a brief animation showing movement within the Yellowstone National Park. And so these resources are what I would call non-contextualized. They don't necessarily have a lesson plan with them. However, they're great supplemental materials, and for some lessons we do incorporate them. As well as the posters and infographics, we have had an educator packet that changes over time as we have resources. Being nonprofits, we don't have a lot of extra funding to ship out resources, but we try. And so that kind of comes and goes. We do have 2 posters that show the velocity field for the Western US and Alaska, as well as infographics showing, what is geodesy, its applications, and more specifically, what GPS can tell us about the Earth, and the many different ways and techniques that's done. We also have a number of interactive data and mapping tools. This is the GPS velocity viewer on the left-hand side, and it's showing every place where you see that blue arrow. That arrow is actually a vector, and down in the lower area you can see what 25 millimeters per year is. Every place where you see a green bubble is a station that is part of the Plate Boundary Observatory that is being analyzed, and that data is available online. And in the right-hand area, you can see the different choices that one can make. And so this is in the IGS reference frame, meaning it's kind of looking at the Earth from the center of the Earth, and all the plates can move freely about it. And so you can see that the central US is actually moving in that reference frame, moving away from Europe. And then you can dig in from there and other places to get data that is ready to use right into a spreadsheet. 2 other mapping tools or data tools that I'd like to highlight is the GPS Spotlight. These are kind of cool because every place where you see a teardrop or different icon, there's a story about the data from that area as well as the scientist story. So there's that human element as well. And then this is an example of an interactive game where students go through and try to figure out how to build a power system so that there can be power through the polar night. We've also developed a number of hands-on demonstrations, and so now we're kind of moving more towards classroom activities. We've put up these hands-on demonstrations, though, it's because we kept doing demonstrations and then having to basically pass on the information verbally and said, maybe we should write this down. And so each one has a video that goes with it, pictures on how to set it up, as well as some of the questions to ask and major concepts that we're covering. And then this kind of leads us into the kind of full-blown activities, lessons, and modules. This illustration here are in yellow are the different lessons that have been developed that you could do as a sequence. It's a recommended sequence, as well as supporting activities that are in green. And then there's a few lessons that kind of span the full spectrum. And so I've kind of split them up into 3 levels of approaches. One is high-level explorations using data visualizations. And so the students are moving right into the visualization without necessarily having to go into the nitty-gritty of how do you go from the data to the graphical interface. And then the next level is where they kind of dive into that data. And then the final level is more in-depth, multiple lines of evidence. And so tying them into NGSS, for instance, using either the poster-based exploring tectonic motions or looking at online tools using like the EarthScope Voyager Junior or the Velocity Viewer, students are already presented with the data in some kind of format. So we've gone from numbers and created the velocity vectors, which are each of those vectors that you see on these maps. And so they're looking at the data, they're analyzing and interpreting it. They're using some computational thinking, maybe some simple math about scale. And in the case of the Velocity Viewer and EarthScope Voyager Junior, they're actually overlaying multiple data sets to kind of get a picture of what's going on in the Western US. So there's a lot of pattern component to it, scale and proportion, because learning that symbols on a map aren't necessarily at the scale of the map. So, moving beyond, just looking at a map and saying, oh, here's a symbol. It's like it means something, and you have to look at the scale bar. And particularly in some of these maps, the scale at the very top is slightly different than the scale at the bottom of the map because of the projection. And then also looking at stability and change, that's kind of when you start moving into some natural hazards component. Going in a little bit deeper, with the sequence, starting with Iceland, so measuring plate motion with GPS in Iceland, and then looking at California. And so you can see we're looking at different kind of tectonic motions, looking at the case of mystery earthquakes in epicenic tremor and slip in Cascadia, and then as well as actually the introduction to graphing. Students that are kind of being more exposed and embedded into more of, what are models, even a model like this, where this is a Hoberman sphere, but talking about the science behind the data and the instruments behind the data. And then again, kind of embedded more of the cross-cutting concepts as well as the performance expectations and core disciplinary ideas. Those I didn't display on here, but that information is available online as well. So the outline for these detailed data dives is to start with kind of demystifying the technology of GPS, because everyone has a GPS. If you have a phone, you've got a GPS on board, and it's just a black box. So, how is it working? And the fact that, if you're underwater, GPS doesn't work. And other places, it can get, the signal can be messed up a bit if you're in a city and there's lots of tall buildings, the multipath, that's the technical term for it. And then exploring the data and at least showing the data. I don't know if you can see my pointer. I can draw. So here is a snapshot from a data set. And I think this is really important because we often work with teachers who come from a variety of background, and they and their students are kind of like, okay, I see the graphs, but what does data look like? And starts off with numbers in this case. And that with GPS data, there's motion in 3 directions, and so they separate out the north-south motion, the east-west motion, and the vertical motion. And then moving then on to to the graphs and how to graph that data. And so from moving from the graphs, then they can start creating vector plots and learning. So now they've moved from a time series plot to a vector plot, which are two different kind of graphs, and that can be a kind of a cognitive shift. So there's a lot of scaffolding to help students make that transition. And then moving it from a graph that's just on graph paper to a map, and then actually using physical models, a little GPS model to help map out with the hand motions, what kind of motion are we seeing here, kind of following that graph. And that really helps with that kinesthetic solidifying of the concepts of what's going on. And then taking this and moving it to a different setting. So here we have Africa, and this is, I believe it's the African reference rate, which means that most of Africa is held fixed, and all these other stations, every place where you see those purple arrows is a GPS station, and compared to the solid part of Africa, it's moving off to the east and northeast. So what's going on there? Well, we could actually map this out with your hands. It's like, this is from my perspective, so it may not actually be coming through, but Africa's staying fixed, and you've got these vectors and they're moving off this way. Oh, what's happening here? Well, I'll let you guys come up with the answer. So they're learning how to interpret the vectors and then move on to some of the societal impact. And then going in a little bit deeper is with multiple lines of evidence in different kind of project settings. So taking the pulse of Yellowstone's breathing volcano and then detecting Cascadia's changing shape with GPS, they're getting even more experience with kind of the full suite of the science and engineering practices and the cross-cutting concepts. So in the case of Yellowstone, the underlying question is, where can the park place a safe long-term research station? And I emphasize the word safe because when I do this in a workshop setting, it's often, hey, let's put the research station right next to where things are happening so we don't have to drive across the park. And the idea is to have a research station that can stay for a couple hundred years and not perhaps have a hydrothermal vent explode right near them. So it's a jigsaw activity, and students become experts in each realm, either the history of the eruption, the current seismicity, formation, and the hydrothermal events. And they look at different kinds of data sets to come up with where they think is the safest part, and then they combine that together. And so this is where the argumentation comes in versus just having explanations. Now you're moving into argumentation of why you're choosing a certain location.
Shelly, it's Aida. Sorry to interrupt. I'm going to give you a 2-minute warning here.
Thank you very much. I am very close to the end.
Great, thanks.
So a very similar process with the Cascadia module. And so these modules do take more time, and that's part of having a very long-term or multiple lines of evidence. It doesn't have to take a long time. And then I did want to share the learning modules from Geodesy Tools for Societal Issues, GETSI. These are geared at this point for introductory level and majors level at college. However, we might have the opportunity to take some of these, maybe not the whole module, but components of it, and to associate NGSS with that and kind of put it in, scale it so that teachers in the middle and high school levels then you can use that right in your classroom without you having to go through that. So I want to thank you. And there are different ways that you can connect with us through Facebook, Instagram, Pinterest, and Twitter. So thanks, guys. And I'm happy to take questions.
Great. So we have a couple of questions that have come up in the chat. Let me just back up to one of them really quickly here. So Keith was asking if the materials that you showed from last year's courses, Shelly, are those available, freely available for people to access?
Absolutely. Yeah, anything that we've taught before, we always have a workshop page, and then those resources are linked in, whether to other parts of our website. But yes, you feel free to take a look at them.
Okay, and then another question that came up was kind of a recognition that you seemed like, as you were going through your presentation, you were starting with the graphs and then going back and talking about the data from there. Is that kind of a course that you're recommending, or was that just the way you put it on your slides? I think that was the question.
You mean starting from a visualization and then diving into what the data looks like? I think it depends on the setting. I have found that, there's a comfort level for both the teachers to be able to teach it as well as the students. Going in and looking at the data and having students graph it right away, let's say using Excel, if there's time, that's a great way to go. But if those resources, being able to use Excel in the classroom isn't available, then starting with the graphs is also great. So they understand, and it's moving, bringing in these math concepts, graphing. And let's say classroom isn't ready for that, then starting from the visualization, it depends on what you're trying to do and whether maybe you're embedding it within your plate tectonics section and you want to start from discovery. So maybe starting actually from the visualization, what's going on here? And then having students come up with their own questions and answers and working together.
Got it. We had a question that popped up in my chat earlier. It actually popped up during Amy's presentation, but Amy, I'd like to hear you respond, but I'd also like to hear from Shelly on this one. So a lot of talk about integrating more quantitative thinking into what's happening. So taking the data, really quantifying it, which is a big piece of NGSS and one that a lot of educators are a little bit uncomfortable with still in terms of the pedagogy and the way to support students in doing that. So first to Amy, then to Shelly, what are your recommendations for supports for educators who are really working hard to integrate some more quantitative thinking into their lessons?
I think I'm unmuted now. So there's a lot of data out there, and there's great tools for helping students do it. I do think it's important to help focus students on the salient aspects of the data so that they can make sense of it, because it becomes overwhelming. The cognitive load sometimes can be a little high, and it is, it is a good idea to walk through some of the data with the students to point out the information and help them start to make sense of it. And we try to in our materials, focus questions so that they're looking at the important features. Shelly?
Yeah, I absolutely agree. In some ways, it's kind of baby steps. And part of each of the activities that we developed was to provide experience in just interpreting these graphs, because although graphing is supposed to be a skill that starts in the 4th grade, you almost have to start over in the 7th and 8th grade. And here we're saying, okay, look at 3 graphs. So literally having to just separate out, just look at the north graph, just look at time versus distance. And, starting from that and putting in a chance to maybe even physically move a model of something, north and south to get that feel. Again, it's kind of that baby steps to go from what is familiar to more abstract unfamiliarness of a graph. And then, putting in a trend line, whoa, that's a big step, So again, moving in, I think, in small pieces is a good idea.
Great. So any specific resources that you would recommend for teachers that would help guide them? Other websites, other organizations? I know CERC has some, Nesta has some.
Yeah, Math You Need When You Need It.
Perfect, yep.
Is
Good one.
a really good place to go check out.
Yeah.
Yeah. The Earth toolkits. Help me out here. You
Earth
guys.
Exploration Toolbox.
Toolbox. Thank you
Yep.
very much. They also help move folks through a nice, the quantitative sequence, so that there's some scaffolding there. And the one activity where we have like introduction to graphing, again, that's its purpose, is to help move students along that path. I think that what I like so much about the Math You Need When You Need It is it shows that integration of, the math skills in an earth science setting. And so many students come into earth sciences like, wait, that's math class. We shouldn't have to do that. And yet it's a big part of what we do.
Yeah. Everybody, John McDarris, thanks for putting those links in the chat. So if you want to grab the links to those two sets of resources, they're in the chat for you there. Okay. Thank you very much, Shelly and Amy, for your presentations. John, if you could put those slides back up, I want to direct everybody to the discussion forum. So with last month's webinar, we started a new feature that we're really excited about because it's a way for the discussion to continue on beyond this little 1 hour section of the webinar. And part of the reason that we decided to start this up is we were recognizing that many people who didn't join the webinar live are accessing it later on in the archived version in the first couple of days. And so they're eager to have a part in the conversation. So we've started a discussion thread, and you'll find a link to it there. You can go back to the April webinar page. And there are 2 prompts that are currently posted up there and eagerly waiting for your thoughts. The first one is, which is more important to you as teachers? Fully described multi-day week modules that pull together multiple lines of evidence as a project, or the components to put together one's own modules. What types of resources do you need? So please elaborate on your choice, thinking about the pros and cons of each. And then the second prompt, what strategies do you employ for helping students work with complex data and models, and how can you help students think critically about data and models, looking at evidence for themselves rather than simply trusting the conclusions of others? So we'd love to hear from all the webinar participants about your experiences and thoughts on that, and I'm sure we'll be hearing from those who are joining the webinar in an archived version on that discussion thread. So please join in on that. Once again, as we close out, I want to show the next webinar. Registration is currently open for May 17th, integrating high school earth and space science into chemistry classes. And thank our 2 presenters, Amy and Shelly, once again, Concord Consortium and UNAVCO. And thank my co-coordinators, Carla McAuliffe, Ed Roback, and John McDarris. Thanks very much. Have a great afternoon, everybody.
Thank you, everyone.